First, on Tuesday evening, February 21st, at Hop Monk Tavern in Marin, Wonderfest presents The Mathematics of Card Shuffling with University of San Francisco's Dr. Cornelia Van Cott. Please visit wonderfest.org to learn about that event and to learn more about this rather sweet nonprofit, Wonderfest. My second point is that audience questions are an essential part of Wonderfest events, and I believe of library events. Here on Zoom, please use the Q&A button down there at the bottom of the Zoom window to type your question right there at the Q&A as opposed to in a chat. All right, it is my pleasure to introduce Dr. Alex Filipenko, Distinguished Professor of Astronomy at the University of California, Berkeley. Alex is one of the world's most highly cited and most popularly beloved astronomers. By highly cited, I mean that thousands of astronomers have referred to his work in doing their work. By beloved, I mean, well, you'll see today. To get just a hint of Professor Filipenko's research accomplishments, consider that he was the only person to serve on both research teams that simultaneously discovered the accelerating expansion of the universe. This discovery earned the Nobel Prize in Physics for 2011 and the Breakthrough Prize in Fundamental Physics in 2015. Professor Filipenko's many personal awards include election to the National Academy of Sciences, winning of Wonderfest's Carl Sagan Prize for Science Popularization, and the highly prestigious Education Prize of the American Astronomical Society. That was just last year. That society is a country's premier astronomical association. Professor Filipenko has appeared in or advised more than 120 television documentaries. With the video education company called The Great Courses, he has produced 5 courses, 5 entire video series. And at UC Berkeley, students voted him Best Professor a record 9 times. Please welcome the highly cited, highly beloved, and heavenly observing Professor Alex Filipenko.
Well, thank you, Tucker, for that very kind and warm introduction. It's a pleasure to be here, everyone. Let me share my screen here now. Let's try that. Okay. Can people see my screen? Tucker?
Yes.
Oh, yeah, very good. Okay, wonderful. Well, so glad to be here today. And through this webinar, I can probably reach many, many more people than if we were to hold the event in person. So, you know, though it's nice to be present in person, the past few years have taught us the virtues of doing these things over Zoom or other webinar friendly media. So I'd like to talk about the James Webb Space Telescope and some of the science that has been gained in really just the first half year or so. It's been over a year since it was launched, but it only really got into position and was fully tested by July of 2022. So really, we've only had half a year of science, and already it's been really wonderful. So, oops, now why is this? Okay, so it was launched on Christmas Day, 2021. The hoped for launch date was 2007. So we were nearly 15 years later than expected or hoped for, but hey, better late than never, right? So, you know, we'd been waiting a long time for this thing. And so what's a few years among friends? People often compare it with the Hubble Space Telescope, which has been up for nearly 33 years now. There are a lot of course, very interesting comparisons. Hubble has done a lot of really great science. But of course, Webb has now taken center stage. And here's a cartoon that recently came out. The new kid on the block, he thinks he's the center of the universe. Webb, I hate him, Hubble. As I'll try to show you, Webb is not a replacement for the Hubble Space Telescope. It's really a complementary mission. And I personally am a Hubble hugger, so to speak, despite also being now a user of the James Webb Space Telescope. So Hubble, you're not gone and forgotten. Nevertheless, the Webb is a much bigger telescope. Its primary mirror is 6.5 meters in diameter, about 21 feet, for those who prefer that system, versus Hubble's 2.4 meters, or roughly 6 feet. And so, you know, telescopes are like gigantic eyeballs. They're collecting the starlight that's raining down upon us. And so the collecting ability is proportional to the area, the square of the diameter, not just the diameter. So JWST, short for the Webb, collects telescopes 6 times faster than HST because of the factor of 6 greater collecting area. Okay, so that's one major difference. The second major difference is that the Hubble is tuned to look primarily at optical light, visible wavelengths. So here we're passing sunlight through a prism. You get the Pink Floyd Dark Side of the Moon album for those who are fans. Anyway, visible or optical light is what we see. And that's primarily what the Hubble sees. It's also good at sampling ultraviolet wavelengths, which are the wavelengths or colors of light slightly shorter than violet. And what's called the near ultraviolet passes through our atmosphere, and that's what gives you sunburns, okay? So Hubble is good at visible and ultraviolet wavelengths. It also samples what's called the near infrared, wavelengths that are slightly longer than red light. They're the near infrared, and Webb samples much more of the infrared, okay? So the infrared is what we often call heat radiation. When you see hot coals and you feel the warmth from them, you're feeling the infrared light. That's what's warming your skin. You're seeing the tail end, the visible portion, the visible tail end of the infrared spectrum. And so you're seeing this orange or red light. But the bulk of the energy from hot coals is coming out in the infrared. And that's the radiation to which the Webb is sensitive, okay? Infrared, near infrared, and a few bits of the long wavelength optical spectrum. But most optical light is not sampled by the Webb, and none of the ultraviolet is sampled, okay? So JWST observes what we call heat wavelengths, and so it complements the Hubble. It's not a successor. It riles me up when in the press, and even some astronomers refer to the Webb as the successor of the Hubble. The Hubble is alive and well. The next round of applications for proposals is due in about a month or so. My team at Berkeley is gearing up to put in a bunch of proposals. And we just finished putting in proposals a couple of weeks ago for cycle 2, year 2 of the Webb. And in some cases, we're studying even the same objects in the infrared with the Webb and in the visible and ultraviolet with the Hubble. Okay, so let me just set the record straight there. Another difference is that the Hubble is in what's called low Earth orbit, only about 340 miles up, okay? There are advantages to that. It can get serviced. It did get serviced 5 or 6 times by astronauts aboard the space shuttle. So even though the Hubble was launched in 1990 and was really ready for launch in the mid to late 1980s, and then there was the Challenger disaster, so everything was put on hold for a while. Its instruments are sort of early to mid 1980s, at best early 1990s instruments, at least for the first complement. But the astronauts went up there and replaced aging instruments with newer instruments, better detectors. And so the Hubble kept on improving And there hasn't been a servicing mission for quite a long time now. So now the instruments are indeed aging, but it kept getting better with time, and that was because of its low Earth orbit. However, because it's in low Earth orbit, it gets a lot of reflected light and heat from Earth. So it's not a particularly cold telescope. And if you want to look at infrared wavelengths, your telescope and the detectors have to be cold, because otherwise they will be emitting a lot of infrared light. Your body emits a lot of infrared, okay? And that would swamp the signal that you want to get from your celestial objects. So Hubble is not tuned to most infrared wavelengths because it would be too warm to be effective. So we had to put the Webb in a place where it could be cooled to a very low temperature and also be in a stable orbit. So a wonderful place to do that is at the so-called L2 point, the second Lagrange point. There was a fellow named Lagrange who used Newtonian physics to figure out that there are three semi-stable regions in the Sun-Earth system where you can place a spacecraft and it'll sit there for a while and it'll gradually wander off, but with a little bit of fuel, you can gently shepherd it back into its semi-stable orbit, okay? Earth is 150 million kilometers from the sun. The L2 point is another 1.5 kilometers out. So that's only 1% farther out from the sun than Earth is. You know, people say the Webb is way out there. Yes, it is way out there compared to the moon, 4 times the distance to the moon. But it's only 1% farther from the sun than Earth is. So given that the sun is irradiating Earth all the time and we're warm and all that, you might think, how can the Webb cool down to very low temperatures? And I'll show you in a minute. But an interesting thing about the L2 point is that it orbits the sun in 1 year, just as Earth does. So the sun, Earth, and the Webb telescope are collinear. They're in this configuration all the time, because even though Earth is orbiting the sun, so too is the L2 point and the James Webb telescope along with it, maintaining this collinearity. Okay, well, how do you get the thing to be cold? The hot side is at 125 degrees Celsius, 260 Fahrenheit. That's the side that's facing the sun. Okay. The telescope is on the cold side at negative 235 Celsius, negative 390 Fahrenheit. So that's a 650 Fahrenheit degree differential. How in the world did the engineers do that? They did it with these 5 layers of substance. I meant to look up the name. It's poly something. Let me look it up on my phone. I wrote it down. Poly polylide, something like that. Polyylide. It's some sort of a substance, and with 5 sheets of this thing, they can establish this 650 degree differential. And it's kind of complicated. You can see that a lot of the light is simply reflected, but some gets through, but then it bounces around between these sheets and eventually escapes from the sides. And that which gets through bounces around some more and escapes, and so on and so forth. So by the time you're at the back end of the 5th sheet, essentially none of that radiation, or almost none of that radiation, is left. So that's incredible. Okay. All right. Well, this whole contraption, the telescope and all these sheets and everything else, is pretty big, but it couldn't be launched on a rocket that way, because the rocket would be way too big, would require, it would have a lot of air resistance, et cetera, et cetera. So all this had to be folded up into essentially a tin can, roughly the size of a bus, but still a tin can. And it all had to unfold and everything in those first month or so. And there was an an anticipated 344 potential single point failures. That made me and other astronomers really nervous, because suppose each of these maneuvers, whatever they need to do, had a 99% probability of success. That sounds pretty good to me, 99% probability of success. But each of these is an independent event. So you have to raise 0.99 to the 344th power to get the full probability of success. And that was 3%. And that's only if I got my 99% right. If some of them were lower, like 97 or 90%, then the overall probability goes down. So before launch, I actually was a pessimist. I didn't think this thing would work. I'm very glad that it works. In fact, it's working better than anticipated. They exceeded their technical specifications. But hats off to the clever physicists and engineers who got all this to work. So, yeah. Anyway, here's basically what it looks like. There's an observing side where the telescope is exposed to everything, including micrometeoroids, little particles that occasionally hit it. Fortunately, not too often. And then there's the sunlit side, okay, and these shields here. But on the sunlit side, there's the solar power array, right? You have to provide power to this thing somehow. And you might think, well, if it's collinear with the sun and the earth, doesn't the earth continuously block the sun? In other words, from the Webb's perspective, don't they see a perpetual total solar eclipse? Now, I'm an eclipse fanatic. That would be pretty cool, but it wouldn't give the telescope much power, right? So somehow they have to avoid it being perfectly eclipsed by the sun. How do they do that? Well, the L2 point is kind of like the L1 point. Now, this is badly not to scale, okay? L2 is not twice as far from the sun as Earth is. It's only 1% farther. But anyway, we're just showing you. Here's the L1 point. Here's L3, by the way. Those are actually pretty easy to understand. The ones that are harder to understand are L4 to L5. You need to learn more physics to understand those. These ones are basically, this one's the easiest. That's where Earth's gravitational pull on an object over here equals the sun's gravitational pull in the opposite direction. So that's sort of a semi-stable point. That's the easiest one to understand. Anyway, we already have spacecraft at the L1 point. SOHO, the Solar and Heliospheric Observatory, okay? It's at the L1 point. It's been there for decades. This is what it does. It has these so-called halo orbits, which are a bit hard to understand physically. Not sure I even understand just how they occur. But it naturally sits there. Occasionally, you need to use a little bit of fuel to nudge the thing back. So JWST is doing the same sort of thing at the L2 point. And that means it's not exactly collinear with the Earth and the sun. It sees the sun. And so the solar panels get sunlight. That's good, right? I recently learned that there's another reason that it shouldn't be collinear. If it were collinear, then it would be looking at the sun's corona, which emits radio waves. And the Webb communicates with Earth using radio waves and radio telescopes. And the radio signals from the sun would be like noise that would swamp the signal from Earth. You know, we're sending it commands, what to observe next, and all that kind of stuff. And the sun's radio emission would swamp the intentional radio signals from Earth. Whereas if the Webb is not looking exactly at the sun, you know, when it points toward Earth, then there's not as much background noise. It's like the stars are up during the day, but, you know, the sunlight swamps them. But when the sun sets, you start seeing the stars. It's a similar sort of thing. I only learned that recently. Okay, so Once the different segments got unfolded and all aligned, they were looking in different directions initially, we got this evaluation image, and everyone said, ooh and ah, look how pretty that star is. No, that's an ugly looking star. That's not what stars look like. They are spherical balls of gas. They don't have points. These spikes are a nuisance, all right? There's 6 main ones, 1, 2, 3, 4, 5, 6, and then 2 smaller ones. Those are a nuisance. They are produced by the fact that light interacts with the edges of these hexagonal segments. And it's a process called diffraction. There's nothing we can do about it. The wave nature of light bends around those borders and spreads out. Moreover, it also bends around these struts that hold up the secondary mirror. And cleverly, 2 of the struts are aligned with these edges. So they add to these spikes here. But one of the struts can't be aligned with the edges because of the geometry. And that's what gives the fainter horizontal one here in this picture. So we have to deal with that. Anytime there's a bright star in the field of view, you want to study all these background galaxies. If the one you want to study, like this one, is clobbered by one of these diffraction spikes, you have to wait a certain amount of time because they then rotate out of the way, and then that galaxy will not be clobbered. All right. But if you only have one observation and it happened to be clobbered, you have to use software to try to remove this thing. And of course, that adds noise because you can't remove it perfectly. So when I show you a bunch of Webb images, don't ooh and ah at the spikes. Those are a nuisance. We don't like them. Okay. Okay. So moving on to the science then. All right. First of all, why view the infrared? Why aren't optical and ultraviolet fine? Well, different wavelengths reveal different physical processes. Okay. And to illustrate that, let me show you 3 images of the same object viewed at different wavelengths of the electromagnetic spectrum. This is a cluster of galaxies, roughly 1 million light years on a side. Here you see it at optical or visible wavelengths. And there are all these galaxies, which are collections of tens or hundreds of billions of stars. All right, great. There you see mostly a starlight. At X-ray wavelengths, you see not so much the starlight, but you see the gas that's heated to millions of degrees by the motions of the galaxies in this cluster. And this gas permeates the cluster and is emitting X-rays. You might have thought that there is no intergalactic gas, especially not hot gas, if you were only looking at the optical wavelengths. So the X-rays teach you something else. Then you look at the radio waves and you see these 2 lobes with these diffuse blobs here and some hot spots. Well, what's going on is there's a supermassive black hole in the middle of this galaxy, and it's got a lot of really heated gas around it and very energetic electrons, and they're spiraling around in magnetic fields, and they emit radio radiation, and they get accelerated into 2 opposite jets, which then interact with magnetic fields, and that causes the electrons to radiate at radio wavelengths. So, this is amazing, but you wouldn't have guessed it from just the optical image. Radio astronomers found these jets, relativistic jets, which means high-speed particles and lobes of energetic electrons spiraling around in magnetic fields. So from the infrared, we can learn new things too, presumably, okay? Secondly, we want to study the evolution of galaxies. How did galaxies like this one form, presumably long ago? How did they evolve with time? Well, to study the first galaxies, you have to look at infrared wavelengths. And the reason for that is that basically the universe is expanding, okay? And although objects like Earth and galaxies are not expanding, they're held together by gravitational forces, and your body is held together by electromagnetic forces, the empty space between galaxies, or more correctly, between clusters of galaxies, is expanding. And what started out as ultraviolet or visible light by the stars that emitted that light gets stretched by the expansion of the universe into the infrared. And the more distant the galaxy is, the farther back in time you're looking, the more stretching has occurred. So you have to look at the infrared wavelengths, even though those early galaxies emitted the light at ultraviolet and optical wavelengths. Okay. So here on Monday, July 11th, NASA had its first press release prior to the Tuesday, July 12th, more extended press conference. And their first image was a cluster of galaxies whose name is SMAXO 723. And this is just an amazing image. Not because of these annoying stars in our own galaxy, not that stars are uninteresting. Someone looking for exoplanets might be interested in that star. But those of us studying galaxies are really annoyed by that star being along the line of sight. And you see, there's a bunch of them. Okay. More interesting then are all these galaxies. So, first of all, this is a tiny fraction of the sky. Imagine a grain of sand held at arm's length. Imagine how small that looks. That's the fraction of the sky imaged here. And yet you can count roughly 10,000 galaxies in this image. 1, 2, 3, 4, 5, 6. I could use up my remaining 20 or so minutes counting galaxies. That would be pretty boring for you, but hey, it's a rather cushy job. They pay us to sit around and count galaxies. Well, this is a representative part of the sky. There's been a number of such images taken, and now we can calculate that within the realm of the Webb, there's something like 1 trillion galaxies. That number was about 100 billion or a couple of 100 billion with the Hubble telescope, but now in the infrared, we can see way more. And in our observable universe, out as far as we can see, there's about 1 trillion galaxies. Wow, that's just kind of mind-blowing. The ones here, many of them are in a cluster. You see there's one galaxy there's a bunch of them. There's sort of fewer galaxies per unit area out here. So that's a cluster. There are lots of clusters out there, and this cluster is bending the light of the background galaxies. You can see all these arcs. That's an example of gravitational lensing. Those are background, more distant galaxies whose light is being bent by the warping of space-time produced by this cluster of galaxies. And again, although qualitatively that's nothing new, just like the number of galaxies only changed quantitatively, nevertheless, we're seeing this now with the Webb, and it teaches us more about not only the visible matter, but the dark matter that permeates this cluster. From the amount of bending, you can see that there's about 6 times as much matter in that cluster as the stuff that emits visible light. And that's not totally new, but it's an affirmation of what we thought we knew. I'll tell you some of the new things here in a minute. There's a few other things that are interesting here, and I'll talk about them some more as well. Some of these arcs correspond to the same galaxy. It's just different images of the same galaxy. And by the way, you can get a nice example of this lensing effect if you just take the bottom of a wine glass. You don't even have to break your glass off, but look at the bottom and write your name on a sheet of paper, and then look at your name through the bottom of your wine glass, and your name will look all distorted and stuff. And you can even make 2 images, 2 copies of your name or part of your name, okay? Because the light gets bent by different ways through the glass. In a similar way, it gets bent along different pathways here, and so you get different images of the same galaxy, and I'll show you the evidence for that in a minute. So you have to be a bit careful when counting galaxies that you don't double count them, okay? Because you are seeing multiple images of the same galaxy here. So it's not fair to just count every image and then estimate the number of galaxies. Okay. Well, here's the first sort of new thing. Images like this led to all kinds of viral headlines. The Big Bang didn't happen. No, this is fake news. It's baloney. All right. It's wrong. Um, this headline appeared largely because there's one or a few astronomers who don't really understand modern astrophysics all that well. And they keep tooting the same horn from a book that they wrote 30 years ago that they haven't changed at all in 30 years, despite all the evidence for the Big Bang that we've gained from various telescopes. Okay. Um, what they were commenting on was a paper that came out within days of the NASA public release of that image I just showed you. Dozens of papers got submitted, and one of them in particular was titled Panic at the Disk's First Rest Frame Optical Observations of Galaxy Structure at Redshift Greater than 3 with Webb in this SMACS field. And I know many of the authors. Indeed, Brenda Fry was a graduate student of ours. She's now a professor at Arizona State. This was a tongue-in-cheek title. I'm not even sure that title lasted in the fully published version. The editors of the journal might not have allowed it. But it's a play on words. There's a there's a, a band named Panic at the Disco. I didn't even know about it. I think my kids knew about it. But it's called Panic at the Disco. It's a pop rock thing. Okay. And so what they said was Panic at the Discs. The interesting thing there is that indeed there are some galaxies that appear to be very young, only a few 100 million years old, and they've already formed well-structured disks faster than galaxy evolution models predicted. So that's great. The Webb has already thrown a new puzzle toward us. Okay. Galaxies, at least in some cases, evolve faster than had been expected. Wonderful. It's not just confirming everything we thought. If that's all that happened in science, it wouldn't be as much fun. But scientific inquiry leads to observations and experiments, which in part confirm what you thought. That's how progress is made. And in part throw you some new bones to make it interesting and delightful. And as our motto for Tucker Hyatt's Wonderfest organization, truth is a great flirt. So hopefully these galaxies will tell us more about the truth of galaxy evolution. They do not negate the Big Bang. Now, what some of these astronomers said was that these galaxies are so well formed, they had to have formed earlier in time than the 13.8 billion years ago, when most of us think the universe was born in a hot, dense Big Bang. But you can read this fellow Jackson Ryan wrote a good article. JWST provides an intriguing look at the early universe, but it's not yet rewriting fundamental theories. Well, this was back in August. I think it is rewriting fundamental theories of galaxy evolution, but it's not rewriting the Big Bang. There the author is correct. Okay. And this fellow Ethan Siegel, he's very good. You can read his articles. Ask Ethan. He's in the news a lot. His articles are quite good, well written. He knows what he's talking about. Ask Ethan, has JWST disproven the Big Bang? No, 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 no. Just no. Can you be more emphatic than that? The JWST has truly blown our scientific minds, but it's a pure crackpot idea that the Big Bang is now disproven. I agree with Ethan. Okay. Anyway, so how do we know these galaxies are that far away, and how do we know some of the images are even of the same galaxy? So for this, we need spectroscopy, and so this is a longer talk than some of my short talks. I did one for Tucker and in Napa for some movie thingy, and that was a short presentation, and Tucker said, Alex, don't talk about spectra. But since this is a longer presentation, I'm going to talk about spectra because they teach us a lot more than just the images alone. So you pass the galaxy light through a prism. I've shown this before when I defined the ultraviolet in the infrared. But now what I'm going to focus on is not just this continuous light, but the fact that you get these dark lines here as well. And if you know how to read spectra, these are like fingerprints of the various elements. This is hydrogen, this is sodium, this down here is singly ionized calcium. There's no need that you need to know about this, but trained spectroscopists analyze spectra based on comparisons with laboratory gas spectra. That's how we know what the gases look like in terms of their fingerprints, okay? So you can plot the brightness as a function of color or wavelength. That gives you a graph. That's what we call a spectrum. So now I'm going to show you unapologetically a bunch of spectra, okay? And they correspond to these galaxies here. Okay, so here's this one. You have to follow this integrated circuit to figure out which one it is. It's that one. And here's brightness versus wavelength in the infrared. And there are these spikes that correspond to hydrogen, neutral hydrogen, and what ends up being doubly ionized oxygen. And the point is, we recognize these spikes. I deal with them every day. And the pattern that they form is easily recognized, but usually these lines are in the visible part of the spectrum. Here they're in the infrared, and they've been stretched so much by the expansion of space that we can tell that we're seeing this galaxy as it was 11.3 billion years ago. So this galaxy is at a look back time of 11.3 billion years. That's already pretty far back compared to the 13.8 billion years that we think the universe is old. So this one's at an age of 2.5 billion years. Let's look at this one. This one's easier to find. There it is. Same spectrum, or by that I mean the same pattern of lines, but shifted more toward the infrared, in the infrared, okay? Corresponding to a stretching that you would expect for a galaxy only 1.3 billion years after the Big Bang. Here's one, that one there. Same pattern. Now the hydrogen line, this one here, for those who are interested, that corresponds to the n equals 3 to 2 transition of the electron in the hydrogen atom. That fell off of this spectrum. It's way out here somewhere, but you still see that hydrogen line and these oxygen lines, and they correspond to a look back time of 13 billion years. So we're within 800 billion years of the Big Bang. And this one here is even farther back in time, even a younger universe, 700 million year old universe. So that's how we study these things, through their spectra. And this one here, you can study in more detail. It exists when the universe was only 700 million years old. There wasn't that much time for chemical processing through stars. Hydrogen fuses to helium, helium fuses to carbon and oxygen, then neon, silicon, iron, and so on, okay? But already the gases in this galaxy show abundant oxygen and abundant neon. And so this is a bit faster than I would have expected, but massive stars can evolve pretty quickly in a 10 million year time scale. So in the first 700 million years, even if the first stars didn't form until 200 million years, let's say, that's 500 million years of time for chemical processing. What this spectrum is telling us is that the chemical processing was sufficiently advanced by 500 million years after the first stars formed that you can already see oxygen and neon, which is interesting, okay? Again, we learned something from that. Okay, so this here shows a special type of spectrum. Here, instead of studying one galaxy or one star by taking its spectrum, the way I showed here, galaxy light, one galaxy forming a spectrum, this is a mode where the telescope can take a spectrum of essentially every object in the field of view. You can see every object has its light spread out. And that leads to some overlap, especially if you have a confusing field like these two objects here probably overlap to form this mess here. But some of the objects don't overlap, and then you can study, a bunch of objects at one time. So here's this arc and that arc, and you might have thought, well, those are two separate galaxies. But here's the spectrum corresponding to each of those arcs. And then if you plot brightnesses versus wavelength, here it is. First of all, it's at the same redshift, which for any two galaxies a priori is unlikely. And it's got the same spectral features, and they even have the same relative heights and stuff. And all these things sort of point to the same fingerprint. This is the same galaxy, but imaged several times because the spectra just look too alike. It's conceivable it's two different galaxies that happen to be at the same location with the same spectral signature and all that, but the odds are pretty low. And you see lots of these things in the field here, and that builds up your confidence that you're seeing a bunch of different images of the same galaxies. Okay, so that's kind of cool. This is an object, a device called a grism, a grating prism that allows you to get a bunch of spectra at the same time. Okay, so galaxies, that's pretty cool. Here's another cluster, which also has an annoying star right next to it. This one I show pretty quickly because ground-based and actually Hubble pictures showed a single star called Arundel, which sort of means the dawn or dawn of time or whatever. It was discovered by the Hubble. Normally, you can't see individual stars that far away, but its light has been magnified by a factor of 1,000 through this process called gravitational lensing. That's pretty cool. Okay, so there it is, a Hubble picture. And what's interesting, the JWST image shows it as well. There it is. So here's a single star 12.9 billion years ago, which normally would be too faint to see, but its light has been gravitationally lensed into something much brighter so we can see it. So that's pretty nice. And we study galaxy evolution not just by looking at the most distant galaxies, including, for example, here's one 11 billion light years away. And it's interesting because it's already a very well-formed barred spiral galaxy. The galaxy evolution people, I think, would have said that's a bit too fast. Maybe not astonishingly fast, because that's 2.5 billion years, but it's a very nice, modern-looking barred spiral galaxy. Kind of neat. Hubble and Webb. Okay, so we look not only at the distant galaxies, but we look at relatively nearby galaxies. This thing is called Stephan's quintet. Really should be called a quartet, because these four galaxies are 290 million light years away. This is an interloper that happens to be along the same line of sight, 40 million light years away. So it's not interacting with those, but those ones are interacting with each other gravitationally, and they're smashing together and forming new stars right there. And gradually they'll come together and they'll look like a train wreck for a while, and then they'll merge to form one super galaxy. So this is a prelude to what's going to be happening to the Milky Way and our nearest big neighbor, the Andromeda galaxy. It's about 2.5 million light years away. It's gravitationally bound to us. It's coming toward us, despite the universe as a whole expanding. This thing is so nearby that it's gravitationally bound. It's coming toward us. We're going to start to merge in 3 or 4 billion years. We will look like a train wreck for a while, and then we'll turn into a bigger galaxy for which astronomers already have a name, milkometa or milkdromeda. Okay. So anyway, Stephan's quintet kind of gives us a prelude to what's happening. Not that we can watch this process for billions of years, but we can look at several clusters like this and compare them with computer and body simulations, where you now use computers to figure out what the galaxies are doing. But you need real life examples at different stages of the evolution so you can test the computer models. Okay. All right. So galaxy evolution. All right. What next? Why the infrared? Well, you can see through clouds of gas and dust more easily in the infrared than at optical or ultraviolet wavelengths. Okay. So let me show you a great example of that. The iconic pillars of creation, one of the most famous Hubble pictures, also known as the Eagle Nebula and M16, only 6,500 light years away. By the way, a light year is the distance light travels in a year. It's about 6 million miles, 10 trillion kilometers. Big distance, okay? But that's the unit astronomers use. So this thing's only 6,500 of these 10 trillion kilometer, 6 trillion mile units away. And we've always suspected that this is a giant stellar nursery, because not only is there gas here, but there's dust. Dust are fine little particles that then become gravitationally bound together in these big clouds, and gravity causes them to collapse and coalesce into new stars, planets, and maybe even ultimately life. So this is a stellar nursery, or so it was thought. And there was Hubble and other evidence from the near infrared. We could see a few stars inside here that are newly formed. But now at middle and far infrared wavelengths, and by the way, this reminds me, okay, every image I'm showing you here is a visible light representation of infrared light, which your eyes cannot see. Just like those radio and X-ray images I was showing you were visible light representations of X-ray or visible light. So here they've chosen a color palette where the long infrared wavelengths are represented as red, middle infrared wavelengths are green, and short infrared wavelengths are represented as blue. So it's RGB. And with RGB on your phone cameras and stuff, right? You can reproduce pretty much any color. So that's what they're showing you here. RGB images of infrared light. I just wanted to clarify that. So here's an infrared image, farther in the infrared than the Webb, and it shows all kinds of newly formed stars. I love this quartet right here. Look at that. Not a hint of them. Well, maybe that's one of them. I'm not sure, but you basically can't see those. Look at this one here. I don't know, maybe, no, it's not that one. It's not that one either, because I'm looking at the edge of the cloud here. It's like here. Maybe it's that one. I don't know. But there's a bunch of them. Look at that one there. Look at these ones here, right? And all the fainter ones. All these stars that are newly formed are still forming. And now we see them in the infrared. So the infrared is great for studying star formation, and stars are often born in cocoons of gas and dust. And so you want to study them at infrared wavelengths because the infrared passes through dust, clouds of dust, much more easily than visible light does. Radio waves are good at this too. You know this because on a foggy day, you might not be able to see an office building or an apartment building a couple of blocks away, but you can still hear your favorite radio stations, right? So infrared and radio, the long waves have an easier time passing through junk. So the Webb is great for studies of star formation. And in the constellation Orion, right, left shoulder, right shoulder, the belt, the sword, the 2 feet. In the sword here is the Orion Nebula. And here is a Hubble picture of the Orion Nebula with the famous trapezium, which are only a few million-year-old stars. But here is a region known as the bar, where there's a whole concentration of dense gas and dust. And it has been studied now or imaged at JWST infrared wavelengths. And here's Hubble versus Webb. And let me just show you that now in a close up. I don't have time to talk about all this because I want to leave a lot of time for questions. But here's a young star inside a globule. Here's a young star inside a cocoon. And there's even a disk of stuff that may be forming planets. Here's a whole bunch of cool filaments and stuff. Here's an annoying 6, 8 spiked star, whatever. Anyway, here's this Orion bar where there's a bunch of molecules, molecular gas and dust and stuff. So anyway, the trapezium cluster is off this way somewhere. Yeah. Anyway, kind of cool. All right. Next thing, you can see colder objects more easily in the infrared than at visible wavelengths because cooler objects emit mostly in the infrared. So again, let me remind you of what I mean. Here's sunlight, lots of visible light. The sun also emits quite a lot in the infrared, actually. That's why you feel the warmth and stuff. All right. Well, here's sort of a representation of a hot, intermediate temperature and cool star. All right. And the colors are exaggerated here, but hot things that emit on their own are blue, cooler things are yellow or even white. Actually, it goes blue, then white, then yellow, then orange and red. By the way, the sun is a white star, not a yellow star. It really is. It's the definition of white light. Okay. Anyway, the point is that the sun has a spectrum that peaks at visible wavelengths, and the distribution of colors and their different intensities is interpreted by our eye-brain combination as being what we call white light. Okay. But a hotter star peaks at ultraviolet wavelengths. Yes, you can see it at visible wavelengths, but here it is 3 times hotter than our sun, and it peaks at ultraviolet wavelengths. So ultraviolet telescopes would see it as being relatively brighter. Conversely, a cooler star, roughly half the sun's temperature, a little bit less than half, peaks in the infrared. And although it emits visible light, it's brighter in the infrared. And some stars are even 1/4 of this temperature. Okay, certainly things called brown dwarfs are very, very cool. And they are very difficult to find at visible wavelengths because their spectrum peaks way off in the infrared here. Okay, next time I'll find another example with an even cooler star. Okay, so let's just do one example of this because I'm running out of time. Here's a dying star called the Southern Ring Nebula. It's only 2,000 light years away. It represents the future of our sun. When our sun becomes a red giant in about 5 billion years, it'll become quite bloated, and the outer atmosphere will be relatively loosely bound to our sun. And there will be all kinds of instabilities in our sun, which will have a series of gentle burps, I call them, which will eject the outermost parts. And then those outermost parts will glow because of the radiation from the leftover hot star. It'll kind of fluoresce, and it'll be called a planetary nebula. Not that it has anything to do with planets, but they kind of look like planets to late 18th century astronomers. But their spectrum clearly was not that of a planet. It was that of a glowing gas, a nebula. So the astronomers called them planetary nebulae. Anyway, so in broad strokes, this is what our sun will look like in 6 or 7 billion years when it starts ejecting its outer envelope of gases. Well, you might have thought that's the dying star because that's the one that's visible in the Hubble pictures. But in the infrared picture, you actually see this star. And it is cloaked by a cocoon of gas and dust. And the dust in particular blocks the optical light, but allows the infrared to come through. And that's actually the dying star. So at infrared wavelengths, we can study not only star formation, but stellar death in this example here. All right. So then coming even closer to home, there are planets in our own solar system. And my colleague Imke de Potter studies Jupiter and Neptune and stuff. And she was quoted as saying, we hadn't really expected it to be this good, to be honest. That is the James Webb, said planetary astronomer Imke de Potter, professor emerita at UC Berkeley. Go Bears. Okay. So, yeah, I mean, as I said, the Hubble, if anything, is performing better than expected. And so here at infrared wavelengths is Jupiter. And it's got all these, clouds and great red spot, which appears white at infrared wavelengths. And then the polar caps here, they're colder than the equatorial regions, and the color palette made them look blue in this particular image. But anyway, Imke is studying the development of storms and things like that. There's also, Neptune with Triton. Here's a ground-based image from decades ago. Voyager 2 overexposed the planet, but showed the rings for which there had been, or there is some ground-based evidence. But it had been more than 3 decades since we actually saw the rings, right? Voyager flew past. And here's the September JWST image, along with an annoying bright star. You get my drift here. So here's the close-up of Neptune with its rings. They're much more easily visible. The contrast is much better at infrared wavelengths. And you can also see 6 of Neptune's moons. And you can see Neptune has storms as well. Well, since I talked about planets in our own solar system, I might as well end on exoplanets. And here we reveal yet another advantage of the Webb telescope. Infrared spectra can reveal the presence of water and possible biosignatures and technosignatures, okay? So how do we do that? We do it during what are called transits, okay? So most exoplanet orbits are random to our line of sight, but those that happen to be edge on allow the planet that's orbiting the other star to pass between us and the star, thereby blocking part of the star's light ever so slightly. 0 should be way down in the floor somewhere, okay, right? Here's 98, 99, 100, okay? So this is just, in this case, a 1.5% drop in the brightness of the star, and that's a lot. This is a big planet. This is a Jupiter-sized planet. Earth-like planets produce a tiny little transit. Nevertheless, it can be detected. And there are thousands of such transiting exoplanets known. No big deal anymore. The Kepler spacecraft tests have found thousands of them. What's interesting is this gray area here. The opaque part blocks the star's light completely. But the gray part here allows some wavelengths to pass through, but produces absorption lines because of electronic transitions for certain photons whose energies can excite those transitions. So the idea is you take a spectrum of the star when the planet is not transiting, and then you take a spectrum of the star when the planet is transiting, and you can compare the 2 spectra and possibly detect atmospheric signatures. Okay, so again, to remind you of spectroscopy, here it is. And this has been done before with the Hubble and even ground-based telescopes. Here we're showing it for this star a couple of decades ago with the example of sodium. Not that sodium is a super good biosignature, although it is needed in our bodies. So, but this illustrates the principle. The star may have sodium lines in its spectrum. Our own sun does, for example. But if the exoplanet has sodium in its atmosphere, then the absorption produced by those atoms will increase the strength of the absorption lines seen in the spectrum, okay? So you'll get slightly stronger absorption lines relative to the continuum. The overall brightness of the star will have diminished by a little bit, but who cares about that? It's the relative amount of the absorption produced by the sodium in that exoplanet's atmosphere. Okay, so that's the basic principle. So the big news was WASP 96b, the exoplanet orbiting a star only 1,150 light years away. And again, this is brightness versus wavelength here in the infrared, bordering on the near infrared. You can actually see this with optical spectrographs. But the point is this: there's a bunch of fairly noisy data. That's okay. This is a hard measurement to make. But the best model fit to the data is with water. We're seeing the spectroscopic signatures of water. And although water itself is not a biosignature, all of life on Earth that we know of is based on water. Maybe in the future it won't be, right? There will be silicon robots and chips. Chat GPT already can do a pretty good job when you ask it the right kind of question. But the idea is that at least biological life on Earth is based on water. So astrobiologists have this mantra: follow the water. Find exoplanets where we see evidence of water, and then look for other more definitive biosignatures and maybe even technosignatures, pollutants, for example, like chlorofluorocarbons. Okay. So now here is a simulated spectrum, okay, of what they might find in the future. All right. The simultaneous presence of methane, CH4, and oxygen, in this case, ozone, which blocks the ultraviolet, that would be very interesting. Not definitive evidence for life, but a possible signpost, because methane oxidizes very, very quickly. Left on its own, it'll combine with oxygen and form other things. So the simultaneous presence of methane and oxygen tells you that there has to be a more or less continuous mechanism forming methane in this simulated exoplanet atmosphere. And although non-biological, that is purely chemical mechanisms, can produce methane, like on Mars, we see variable amounts of methane, but I don't think most astronomers think that that's good evidence for life on Mars. So there can be just non-biological, abiological chemical processes. There are also biological processes, right? Decay, bovine flatulence, Carl Sagan called it. By the way, with cows, it turns out to be mostly burps, not so much their farts. Didn't know that until reasonably recently, but yeah, you can look it up. Tell me if I'm wrong. I think it's mostly burps. But anyway, it's a possible biosignature. And so then astronomers would point even more telescopes at this particular exoplanet rather than just blindly looking everywhere. And you might even, like I said, find pollutants or something like this. So that's the holy grail, and certainly it's one of the great goals of the Webb, to find possible signatures for life. So I went on a bit longer than expected, but that's because I wanted to really thoroughly explain things. And I also know that we have an hour and a half, not just the usual 1 hour. So that gives us a good 20, 21 minutes. But stay tuned for many incredible results. Initially, it was thought maybe it would last 5 years, but that was dictated on the premise that they would run out of fuel to nudge it back to the L2 point if it wanders away, right? But they aimed so well in getting it to the L2 point that they didn't have to use up much fuel. It was like a hole in one almost across the US, just a little bit of cheating at the end from San Francisco to New York or whatever, okay? Just a little bit of cheating at the end. So they saved a lot of fuel, and that means that they'll be able to nudge this thing back to the L2 point for a longer time than anticipated. And it looks like, despite the micrometeorite hit in the first month that was bigger than anticipated, there hasn't been a whole slew of those things. There's been smaller ones. And they also tend to, aim now in a way that the ones that come in are coming in at a lower speed rather than directly head on, but being in the opposite direction. Okay. That means the kinetic energy is less. And so the amount of damage to the mirror is less. So we're cautiously optimistic that the lifetime of the Webb will be 2 decades, folks. So cross your fingers. Should be great. I'm now open for questions in the Q&A room, and holy moly, I see that there are 44 of them. let me quickly go through them here. Will the Webb be able to pick up the spectrum of free oxygen on exoplanets? Yes, as I just explained. Do the expanding galaxies point back to a singular point in the universe? Is there anything of interest in that point? No. Think of the universe as an expanding balloon. Yes, there's a center to the balloon, but that's not part of the balloon. That's not the universe as I defined it. So to be very brief, because I see so many questions here, we think our 3D space bends around a fourth spatial dimension where there might or might not be a center. Okay, we don't know whether the universe is finite or infinite, but that's not part of our universe. So the Big Bang happened everywhere. There is no center. Okay. Can the Webb be serviced? Probably not easily, but people, clever engineers are thinking about it. Okay. So maybe. What is the Webb's power source? The sun. I authored the Webb Observatory spec and termed it the successor to Hubble. Please change that when talking with people outside about it, outside of technical environment, since for most folks, that's effectively what it is, even though Webb does a variety of things. Yeah, but please, for Hubble's sake, change your website. I object. I'm serious here. I object to being called a successor. First of all, the Hubble is still up there. Second of all, it's still useful. Third of all, the Webb does different things. Okay. So if you could change your website, I would appreciate it. But thank you for reaching out to the public and trying to teach them about science and the Webb. I do appreciate that. But if it's easy to change your byline or whatever, if you could. So trillion galaxies in the universe or in the sample field? No, just 10,000 in the sample field, but we now have many such fields and we can extrapolate to the whole universe. Okay. What book is that? The 30-year out-of-date one. I hate to mention it, but it's called The Big Bang Didn't Happen by Eric Lerner. But please don't believe it. Okay. Why do some galaxies look like or orbiting an annoying star? It's just the luck of the draw. The stars in our own galaxies are just along the line of sight by accident. They have nothing to do with those very distant galaxies. Okay. First, Panic at the Disc is hilarious. I agree. Second, the actual question, does humor often show up in these kinds of writings? Sometimes, but sometimes the editor says that's just too humorous or that's just too, I don't know. I'd have to look up that particular paper, whether the editor allowed it. What kind of prism spreads infrared light? I'm not sure. I'd need to look up what kind of a grism they're actually using. Okay. If you want to look back in time, good question. If you want to look back in time even further, should you look in the microwave or radio? And is it size constraints preventing a space telescope of these wavelength designs? Okay, Ashley. So yeah, to look further back in time, we are looking at radio wavelengths. It's called the cosmic microwave background radiation, the CMBR. It's the afterglow of the Big Bang. It comes from when the universe was only 380,000 years old. And a redshift, if I can get technical here, of nearly 1,100, whereas the highest redshift galaxies Webb has found are only about 10. So the point is that afterglow of the Big Bang, it's before galaxies and stars had a chance to form, but it's coming from a time when the universe went from being opaque, like the sun, to light traveling through it, to being transparent, like the visible edge of the sun to having light go through it. So already we're looking back farther in time using radio telescopes. The problem is nothing interesting. No stars or galaxies had formed. I shouldn't say nothing interesting because there are little freckles in the microwave background that are highly interesting, okay? But no stars or galaxies had formed. And then going back to your question about radio telescopes in space, they are being planned, and the microwave telescopes like Planck and the Wilkinson Microwave Anisotropy Probe, the WMAP, those are radio telescopes in space. But some people call microwaves to be a distinct part of the electromagnetic spectrum. To me, microwaves are just part of the radio spectrum, but I must admit, some engineers and physicists and astronomers consider microwaves, that is long infrared or short radio, to be their own separate thing. So yeah, most radio telescopes are even bigger. So then it becomes a problem of cost, basically. How do you get this giant thing up there? But people are working on it, clever ways of making less expensive radio telescopes. Okay, regarding the question of Earth's shadow, while the Webb is always opposite the Earth, Sun, Moon system, just not eclipsed by Earth, if it were permanently eclipsed, JWST solar array wouldn't be able to provide the electrical power. Yeah, that was my whole point, David. I'm not sure if you joined my talk late, but I said, first and foremost, the thing is on a halo orbit, so it's not perfectly collinear. In that way, the solar panel can see the sun. So I think I did make that point, perhaps not clearly enough. And then the second point was simply that the sun's radio emission would cause too much noise. Does Webb have application within our own galaxy? Sure. All the exoplanet atmospheres that are being studied, those are only 1,000 light years away or hundreds of light years away. The star forming regions, the Eagle Nebula, 6,500 light years away. Our galaxy is about 100,000 light years. So anything less than about 100,000 light years that I showed, that's in our galaxy. Is there any difficulty in distinguishing the spectrum from a galaxy/star from the degree of redshifting? Is the distance ever in doubt in a way that could mean a misinterpretation of the spectrum? Basically, no. Things in our own galaxy are moving toward us or away from us slowly, okay? The things that are far away are moving quite fast. Now, there are a few stars that have been ejected from our galaxy. They're going at greater than the escape speed, but they're clearly stars moving away from us. There are also galaxies, in our local group that are gravitationally bound to us and thus are either at any given instant moving toward us or away from us. But again, we can distinguish those galaxies as being, local group galaxies. Maybe Arundel is it. Oh, let's see. There was a previous question. Sorry, I joined late, so don't know if you covered it already. At the start of Webb, scientists were ecstatic over a dot Webb captured. I didn't understand their explanation, but they said it proved it was either another galaxy or universe. I can't remember. Do you know what I'm talking about? It wasn't another universe because we don't know of any way of looking outside our universe. If it was just a tiny little dot, it may have been Arundel, as Alexis says in the next thing. But it might have been one of these little dots that was just already a well-formed galaxy, more well-formed than we anticipated. Then someone, let's see, it moved away, but someone said, yes, that's it. And then that part of the conversation somehow moved away. Okay, will the Webb telescope have the ability to ever see outside the observable universe? No, by definition, light comes to us from the observable edge of the universe, but we have no reason to believe that that's the physical edge. Do all stars belong to a galaxy, or can you have erratic stars that occupy space without being part of the galaxy? Yeah, stars get ejected from galaxies sometimes by gravitational interactions. For example, if you have a binary star and another star comes in, that other star can steal energy from the binary and be flung out of our galaxy. So we do think they're intergalactic stars. Um, so now, with the updated understanding that there are now 1 trillion galaxies instead of a few hundred billion, that means there is a lot more mass in the known universe. That could change the outlook of whether the universe will continue to expand forever or eventually slow down and start to contract again. Good try, but we already knew the mass density of the universe quite well. The question was how much of that gas formed into galaxies and how quickly. But there are a number of arguments that already give us the matter density quite well. And that, in terms of protons and neutrons and things that we're made out of, is only 5% of the cosmic pie. 25% is dark matter that does not consist of protons and neutrons. That's the exotic dark matter. And then 70% is the dark energy, which is not even matter at all, which is accelerating the expansion of the universe. So it doesn't change our outlook of whether the universe will continue to expand forever. Then how much of the sky can it see over a year, and how long would it take to do a full sky survey? The Webb samples only a tiny fraction of the sky, so it's not designed to be a sky survey. However, in a couple of years, the Vera Rubin telescope in Chile, an 8-meter telescope, will start a sky survey, and they will sample the entire southern and part of the northern sky every 2 or 3 days. And that's like a gigapixel camera, which is just fantastic. And already the Zwicky Transient Facility at Palomar Observatory does the northern sky every 2 days or so, just not to such deep limits because it's a smaller telescope. But Webb is designed to study in detail objects that astronomers have found in sky surveys. Do scientists expect JWST will help to unravel the nature of dark matter and dark energy? Maybe, but there I'm not as optimistic because you need samples of very large numbers of objects. And so the Vera Rubin telescope and the Nancy Grace Roman telescope, which will be launched around 2027 or 2026, that do surveys of lots of type 1a supernovae and things like that, they will be better because we now need large samples of objects, and time on the Webb is so precious that it's just not going to sample enough objects. Now, maybe I'll be proved wrong, but at least I haven't thought of ways to use the Webb to give us the aha moment. What are dark energy and dark matter? Regarding the star that's 12.9 billion light years away, you said the star's image was magnified by 1,000. Is there a way to determine how large it actually is? If so, how big is it relative to something familiar like the sun? Yeah, so this is almost certainly a giant star already, several times bigger than our sun. The factor by which its light has been magnified comes from the models, basically, of the gravitational lensing. That is, we know the distribution of galaxies and dark matter pretty well from having studied that cluster and the amount of lensing that it produces of background galaxies that we have already seen. So you can make maps of where the dark matter is and where it should produce a particularly high magnification. And that star appears right at one of the places called acoustic, C-A-U-S-T-I-C, where there should be a lot of magnification. But to some degree, I think that number is model dependent. And so I don't know whether it's a factor of 1,000 or 2,152 or 963 or what. So because things are somewhat model dependent and we do not yet have a spectrum of that star, we don't know exactly what kind of star it is and how big it was. Okay, what elements existed just prior to the Big Bang? Nothing existed prior to the Big Bang, at least not in our universe. Our universe was born with the Big Bang. But in the first 3 minutes of the Big Bang, hydrogen and helium and their various isotopes, light hydrogen and light helium, for example, were produced, and a smidgen of lithium. And that's all, folks. The heavier elements were produced through nucleosynthesis in stars. Is there any plan to use gravitational lensing as a telescope? Yeah, already it has been. We observe Arendelle and some of these ancient galaxies because their light has been magnified by this wonderful telescope that nature has provided for us, right? So we're already using them. And then a very important question, why it is important to study all this? I like that question. I'll give you a very short answer because we're running out of time. But first, we're the only creatures we know of, at least on Earth and in our known universe, that have the mental ability and the curiosity to, first of all, ask questions like this and then find ways to answer them and to build machines with our opposable thumbs with which to answer them. So although there are many ills in the world, to some degree, humanity would be selling itself short if some small fraction of us were not investigating questions like this simply because we can. We're humans. Second of all, you never know what kind of unanticipated spin-offs these kinds of studies could give. Quantum mechanics a century ago was developed to understand the nature of light and the stability of the atom. Atoms shouldn't exist. No practical applications in mind. Fast forward 1 century, and you could not imagine life today without all of our devices and lasers and stuff. And thirdly, it's this kind of science, the Hubble images, the landing on the moon, things like that, that excite kids to go into STEM fields. And most won't become professional astrophysicists, but some might be more motivated to pursue STEM fields and then to go on to more immediately useful professions, immediately useful to society, like engineering and applied science and medical physics and medical and computer science and things like that, right? So it's the stuff that turns kids on. So that's my quick elevator pitch. Will there be a book on these images? Oh, I know of several authors who are already writing books on the web, but you can just go to the NASA website and they love to show these images and they appear on Astronomy Picture of the Day, and just Google James Webb images. Are the annoying spikes present in most stars? Yeah. So they're on all stars that are bright enough. In fact, they're in the stars that are faint too, but it's just the contrast of the images doesn't show them. If Einstein were alive today, what do you think he'd be studying with regard to the universe? I think he'd be pretty astonished by the accelerating expansion of the universe, and he would be trying to figure out whether his cosmological constant, which he dreamed up for the wrong reasons, might end up being the right answer. How could JWST help figure out the geometry flatness of the universe? That's done more by the radio telescope studying the little spots in the cosmic microwave background radiation, okay? So probably not so much with Webb. Then you mentioned the single star. There was a lot of interest in Arendelle. Brighter due to gravitational lensing. Is it really brighter, or is that the footprint of the star is bigger or magnified? But the brightness is the same. Okay, there are two related concepts here, which is luminosity. That's the power or oomph of a star, how much it intrinsically puts out. And then there's apparent brightness, which is how bright the thing appears to be. It appears to be much brighter than it should have, but that's because this lensing galaxy and cluster took some of the light rays that would have missed us and bent them around to hit our telescope. So it's light that would have missed that then gets focused to our telescope just because we happen to be collinear with it. It's not collinear with some alien that lives somewhere else. They have some other gravitationally lensed star. And then finally, because we ran out of time, is it arrogant for humans on Earth to think there's no other intelligent life in the universe similar to humans? I think it's arrogant. I think we're not the only ones out there. However, and this may surprise you, I think intelligent, mechanically able life is far more rare than some of my colleagues like Seth Shostak at the SETI Institute. He has to think they're common because otherwise, he'd be wasting his life looking for them. But I think they're rare. We may even be the only ones in our galaxy, or one of only a handful, not in the observable universe, but in our galaxy. And just briefly, my reasoning is that there's been tens, if not hundreds of billions of species of life on Earth during the nearly 4 billion year history of life on Earth. There's no evidence that anything has come close to our level of intelligence and mechanical ability. Second of all, we appeared as early hominids 4 million years ago, and as Homo sapiens 250,000 years ago, out of the 4 billion year history of life on Earth. So for most of Earth's history, intelligent aliens flying by would have said there's nothing particularly intelligent or mechanically able on Earth. That tells me that this was an evolutionary fluke that is very, very rare. Thirdly, though we have improved the standard of living for hundreds of millions of people over the past century, we're also quite clearly not very good at taking care of Earth. And moreover, we're the type of creature that has developed technology that could either intentionally or unintentionally end up destroying us, or through neglect. So we might be flashbulbs in the night, and if other in the night of the Milky Way galaxy, and if other intelligent creatures tend to have these kinds of humanoid characteristics, then they too are flashbulbs in the night. And then finally, if they were common, then there's the Fermi paradox. If there's 100,000 of them in our galaxy, why aren't some of them so advanced that they've colonized our galaxy and that they've made their presence known in an obvious way to us? Indeed, why aren't we the aliens? So for those 4 reasons, I think we're very, very rare, and we're privileged to be able to study the universe with these incredible telescopes. So thank you very, very much. And we should take care of Earth, of course, so that we can continue to thrive and to study the universe.
Wow, Alex, this has been fantastic. You kept up with an impressive onslaught of beautiful questions. Thank you for trying. Thank you for working so hard with us. Let me bring this event to a close by offering 3 big thank yous. First, to you, our Zoom audience, and especially the questioners. Thanks so much for being here. Second, to the San Francisco Public Library for hosting today's Zoom. And third, of course, to Cal Professor Alex Filipenko for keeping us wondering and looking up. Astronomy is looking up. The library will be sending out a recording link to all who registered. And now I bid farewell, and maybe we'll see you at a Wonderfest event coming up soon.
Great. Thank you very much, Tucker.
Thank you, Alex.